All right, let's read problem number 14 here. It says a rectangular piece of carpet covers 200 square yards. The width is 9 yards less than the length. Find the length and the width of the carpet. Round to the nearest tenth of a yard. All right, so whenever you're given a word problem, if you can draw a picture, try to draw a picture. It always just helps you to better focus in on the situation. So I'm going to draw a picture of a rectangle here on my paper, and I'll shift my doc cam in a moment here so you can see this. We know what they tell us that the area of this carpet is equal to 200 square yards. And it indicates that the width is 9 yards than the length. Now, based on how this second sentence reads, the width depends upon the length. That being the case, I'm going to declare my variable. I'm going to call it L. I'm going to let L be equal to the length of the rectangular piece of carpet. And what would be a variable expression that would represent 9 less than my length L? So 9 less than my length L could be expressed as L minus 9. That will be a variable expression that represents the width of this rectangular carpet here. All right, so here we go. This is what I have so far on my paper. I have a picture of my rectangular carpet, the area of which is 200 square yards. The length I'm going to call L. I'm going to actually label this side, and this side is the length, and my width is going to be L minus 9. All right, how do we find the area of a rectangle? The area of any rectangle is always computed by taking the length and multiplying it by the other dimension, the width. So therefore, the area of this rectangle is going to be the length, which is L, times the width, but another name for the width is L minus 9. But they tell us the area is 200 square yards, so therefore 200 is equal to L times L minus 9. And now I can solve this equation for the variable L. To do so, we realize that we do not have a linear equation. In fact, after distributing, of which we need to do on the right side, we discover that we have a second degree term here. And so we really have a quadratic equation we're going to have to solve for the variable L here. So this equation will have two solutions. To solve for the two solutions, last week we touched base with different ways of solving these types of equations, these quadratic equations. The factoring method usually is the quickest way to go if you can do so. So I'm going to zero my equation out by subtracting 200 from both sides. And I'm going to spin my equation around here. So after subtracting 200 from both sides, my quadratic equation looks like this. Now we're going to ask ourselves, can we factor this trinomial on the left side of our equation? Are there two factors of negative 200 that sum up to a negative 9? Do they exist? Well, what are factors of negative 200? I mean, you can start listing some. Negative 1 and 200, negative 2 and 100. 3 don't go into 200 evenly. 4 does. Negative 4 and 50. Negative 5 and 40. 6 don't divide into 200 evenly. 7 doesn't. 8 does. 8 does. Negative 8 and what? 25, I believe. 9 does not divide into 200 evenly. 10 does. Negative 10 and 20. 11 does not. 12 doesn't, 13 doesn't, 14 doesn't, 15 does not divide into 200 evenly, 16 does not, 17 doesn't, 18 doesn't, 19 doesn't, and 20 does. This is the list of factors of negative 200. Now, do any of these factors in this list sum up to negative 9? Any pair of these factors? Do they add up to negative 9? It does not appear that we have any combination of factors in this list that add up to our middle coefficient of negative 9. Because of that, ladies and gentlemen, it does not appear that we can factor this trinomial. But nonetheless, that's not to say that this does not have two solutions, because this second degree equation must have two solutions. We just have to use a different technique to find them. Completing the square is not a favorite, takes time, so why not just use the quadratic formula? The quadratic formula can solve this quadratic equation. We need to know what, of course, our equation has to be set equal to 0, and it is. You have to identify A, B, and C for the quadratic formula. My A is the leading coefficient of 1, B is the middle coefficient of -9, and C is the constant term, which is -200. So we feed things into the quadratic formula. So L is equal to the opposite of B, the opposite of -9 plus or minus the square root of B squared, -9 squared, minus 4 times A is 1, times C is minus -200. And all this sits over 2 times A, which is 2 times 1. So our two solutions for L are going to come from simplifying this. We have +9 plus or minus the square root of. Can anybody dial this quantity up for me underneath the square root? This is called the discriminant of the quadratic equation, this B squared minus 4AC. Anybody bring that up for me, what that would be? If you can dial that up there. Let's see, that would be 81. -4 times -200 is 800. So it looks like 81 plus 800 would be what? Looks like 881, correct? Make sure you're able to get that. Now, therefore, we're going to have two possible solutions here. One solution is going to be 9 plus the square root of 881 over 2, and the other one's going to be 9 minus the square root of 881 over 2. I want you to get on your calculator, and to the nearest tenth, I want you to compute both of these here, to the nearest tenth. So as to stay off a logical error, you might want to close your numerators inside parentheses here. All right, go ahead and see if you can dial these up and let me know what you get. 9 plus the square root of 881 divided by 2. What does that give me? To the nearest tenth, 1 decimal place. What would that be?
38.7.
Okay, what was that again?
38.7.
38.7, okay. 38.7 yards. Now let's work the second one out here. Just change the plus to a minus sign. What do we get here? The second one.
-20.7.
Okay, -20.7. Now, although -20.7 is a solution to this quadratic equation in the variable L, ladies and gentlemen, in the context of our problem, this has no meaning because we declared L to be what? The length of the rectangle, and lengths are not negative. So we'll toss this out. It makes no sense. And therefore, the length of this rectangle would have to be 38.7 yards. That would be the length of this rectangular piece of carpet. 38.7 yards. And therefore, the width is going to be the length minus 9. So what's 38.7 minus 9? I believe that's going to be what? 29.7,
29.7.
I believe. And that would be the width of this rectangular piece of carpet is 29.7 yards, and the length is 38.7 yards. Any questions how we found the dimensions of that rectangular piece of carpet there? We had to solve a quadratic equation to do so, though. All right, so that's a classic problem involving the use of a quadratic equation to take care of business in the real world. All right, so that's number 14. That was on page 130. Let's see if we can maybe try number 22. Let's go see what 22 is all about here.
Is this all part of 1.5?
Yes, this is
Okay.
1.5. I'm just trying to do a couple of these application problems on a 1.5, and then we'll get into 1.6 here. All right, number 22, we're going to try to work a problem out like this. Lorene plans to make several open-topped boxes in which to carry plants. She makes the boxes from rectangular sheets of cardboard from which she cuts out 6-inch squares from each corner. The length of the original piece of cardboard is 12 inches more than the width. If the volume of the box that she constructs is 1,728 cubic inches, determine the dimensions of the original piece of cardboard. Okay, that will enable her to construct these boxes here for for the purpose of carrying these plants around here. Okay. Well, your author did give you a picture of the rectangular piece of cardboard that is to be used. And I'm going to try to put that on my paper here so that I can use it for argumentative purposes. Notice we're going to cut out square corners of the size of 6 inches by 6 inches. Okay, so 6 inches by 6 inches are the sizes of the squares that are going to be cut out on each corner. All right, now, when she cuts these square corners out, she's going to leave behind this figure here. So envision, literally cutting these out, cutting these corners off here. You're going to be left with this shape here that we're going to fold up about these dashed lines here. And when you fold these sides up about these dashed lines, you're going to create a box. So in general, this is what your box would look like in 3D, and you got to use a little bit of imagination here, ladies and gentlemen. This actually goes behind my page here. That's my box. Now, notice in this problem here, they do give us the fact that the volume of the box constructed must be 1728 cubic inches. So the volume of this box is 1,728 cubic inches. They tell us that. How do we find the volume of a box or a rectangular prism, as they're sometimes referred to? Anybody know how we find the volume of a box? What's that? I think I heard it.
Length times width times height.
Length times width times height. Okay, the product of 3 dimensions. So maybe we could call this maybe the width, and call this dimension that goes behind the page the length, and then this dimension would be the height right here. Okay, multiplying this by this by this will generate the volume of that box. Now we don't know what the the width and the length is and all that stuff here. We don't know anything about that. But what we do know here is, according to what the problem says, it indicates that the length of the original piece of cardboard is 12 inches more than the width. And based on how that sentence reads, it reads as if the length depends upon the width. And because of that, I'm going to start my declaration part of my word problem out by saying let W be equal to the width of the original piece of cardboard. All right. So therefore, ladies and gentlemen, I'm going to call here to here W inches. That's the width of the original piece of my cardboard before I made my corner cuts here. But what about the length? Well, it says the length what? It says the length of the original piece of cardboard is 12 inches more than the width. So what variable expression would represent 12 more than our width W? Well, that would be W plus 12 then. So W plus 12 is a variable expression that represents the length of the original piece of cardboard. So now we have an expression for the width and the length of the original piece of cardboard here. All right. But ladies and gentlemen, how do we find the volume of the box here? Well, we need to understand that the volume of my box is going to be what? What would be the, now we got to be careful here. See, this is the width of the original piece of cardboard, and that's the length of the original piece of cardboard. But as far as the box's dimensions are concerned here, I don't want you to confuse this W, this width, with the width of the original piece of cardboard, because the width here is not equal to this width here. It'll be equal to this width minus cutting off the squares here. So we got to be careful here in how we, name these variables here. So I'm going to I'm going to vanquish that there. I'm not going to call that the width there. Okay. I'm not going to call that the length here. My whiteout is all but dead here. Must go to dollar store and buy more whiteout. All right. Okay, so what is going to be the width of the box left behind after we make these corner cuts here? Well, I have W inches, but I'm cutting out what? 6 inches here. And I'm cutting out 6 inches this way. So what then, ladies and gentlemen, would represent the width? It's going to be W minus what? Minus 6 and minus 6. So what is this dimension going to be here then? Here to here. It's going to be W minus 6, W minus 12. That's going to be W minus 12. That's going to be this dimension here, W minus 12. The length of my original piece of cardboard is W plus 12, but I'm cutting out 6 inches here and cutting out 6 inches here. So therefore, what would be the length of my resultant cardboard? It's going to be W plus 12 minus 6 minus 6. That's to say W plus 12 minus 12, which is to say just W. And so there we go. So the length would be just what? W. Okay. Would be just W here for the resultant box. Now, what's going to be the height of this box? Anybody want to weigh in as to what the height would be?
6 inches.
Yep, 6 inches, because, you know, we fold, you know, this about this dashed line here. And when you fold it up, this is going to be the height. That is 6 inches there. Okay, that is the height. So 6 inches. All right. So how do we find the volume of this box now? Well, volume is length times width times height. So we'll take W minus 12 times W times 6. All right. So therefore, the volume of the box is going to be, and I'm going to put it in a certain order. I'm going to say 6 times W plus 12. W minus 12, excuse me. So height times length times width. But they tell us that volume is to be 1728 cubic inches. And so, ladies and gentlemen, we now have an equation that we have to solve for W. And this is the equation, and this turns out to be a quadratic equation again, because we're going to have to distribute the 6W inside the parentheses here. So we'll have 6W squared minus 72W. That's equal to 1728. Now, to solve this quadratic equation, I'm going to zero the equation out by subtracting 1728 from both sides. And when I subtract it from the right, of course, the right goes to 0. So this now is the quadratic equation that we're going to have to solve for W. And keep in mind, when we solve for W, ladies and gentlemen, W is going to be the width of the original piece of cardboard before we did the corner cuts. Okay, so it's very important to know how we're declaring these variables here, what they represent. Now, we could use the quadratic formula here, or, you know, you could probably, you know, factor this trinomial if you wanted to. I'm probably just going to maybe use the quadratic formula. So my A would be equal to 6. My B is the linear coefficient, which is negative 72, and my constant term is negative 1728 at the end. Feeding things into the quadratic formula, my width is going to be the opposite of B. That's to say the opposite of negative 72, plus or minus the square root of B squared, which is negative 72 squared, minus 4 times A, which is 6 times C, which is negative 1728. And this is all going to be divided by 2 times A, or 2 times 6. All right. The opposite of a negative 72 is a positive 72, plus or minus the square root of. Now, I want you to get on your calculator and dial this up for me. What would be this discriminant of this quadratic equation here? This is the quantity B squared minus 4AC. And this discriminant can tell us what type of solutions to expect for the quadratic equation. I'm going to try to post a little short video that will describe the discriminant, because unfortunately, I did not have time to go over this discriminant here last week. But anyways, can you get on your calculator and dial this up here and tell me what this all evaluates to underneath the square root? So what would be that discriminant?
46,656.
All right, so you got 46,000. What was it now?
656.
Okay. Did anybody else get this? Can we get another confirmation on this? Anybody?
Yes.
Okay, so that looks good. All right, so ladies and gentlemen, we need to simplify this now. We're going to have two solutions for this quadratic equation for W, but we have to see if they both are relevant for our situation. So therefore, I want you to get on your calculator now, and I want you to dial up 72 plus the square root of 46,656, all divided by 12. Tell me what this one gives you. And then I want you to do the other one, which is 72 minus the square root of 46,656 divided by 12. And if we get one of these as being a negative answer, we're going to throw it out, because W represents the width of a piece of cardboard, and he can't have a negative length. So I'm curious to know which one we're going to have to toss here. Tell me what we get for this first one here.
3,894.
3,894. 3,894.
Oh, I'm sorry. I didn't do the square root. My bad.
Yeah, that sounds way too large. Yeah,
Sorry.
double check that. Because our volume's only 1728.
$24.
Oh, 44?
24.
24 inches. Can I get a confirmation on this from anybody else?
Yeah, I got 24.
All right, let's try this one now. Turn it into a minus and tell me what this computes to now. This one right here.
I got -12 for the minus.
Okay, -12. Anybody else get something like that? -12.
I also got -12.
Yeah, it seems like this would be negative. Yeah, we're going to toss this one out. Although it is a solution to this quadratic equation and a variable W, don't get me wrong, it is a solution. It has no meaning in the context of our situation here. So we're going to toss this, and we're going to go with this. This would be the width of your piece of cardboard before you made the corner cuts, 24 inches. So the piece of cardboard is 24 inches. And what would be the length of the original piece of cardboard before cutting out the corners? That would be 24 plus 12, which is to say it would be 36 inches. And there you go, ladies and gentlemen. We would have our width and our length of the original piece of cardboard after, before making the corner cuts, okay? And the dimensions of this cardboard, coupled with the corner cuts, will then afford us to build a box that has 1,728 cubic inches guaranteed. All right. Now, I mean, suppose you have an industry, that cranks out maybe thousands of these boxes every single day. And, the price per box may not be much, but, if you're cranking out millions of these things or billions over a course of a year, you're talking about a lot of money here, okay, in these boxes. And so obviously you probably want to do your homework and make sure that, you can minimize the cost. And part of minimizing the cost is to minimize the size of cardboard needed, okay, to construct this box that has the desired volume. And so there's a lot more science than you think, in the industry out there. Somebody's doing the math behind the scenes, okay? Those are normally actuaries, people that have math degrees, that are helping companies out to make informative decisions so as to minimize cost and maximize profit. And that's really all the bottom line out there in the real world. Okay, so there you go. Any questions about how we by solving this quadratic equation, we're able to come up with the correct dimensions of that piece of cardboard to construct this box here? All right, so that was one like number 22. I got one more lined up here. Number 35. I want to take a peek at that one. And it reads this way: the population P of a culture of Pseudomonas aeruginosa, whatever that is, it sounds nasty. Probably wouldn't want to get that. Bacteria is given by this quadratic function here. P represents the population of that bacteria. T represents time in hours since the birth of that culture, if you will, the initial time period. So we do have a quadratic function, and they're going to ask us a question here. It says, determine the time or times at which the population reaches a level of 600,000. They want to know how many hours it's going to take for the population to grow to 600,000. Well, to answer that question, we're going to let what be equal to 600,000? Are we going to let P be 600,000 or T? What do you think? What are we going to set equal to 600,000?
P.
Yeah, we're going to set P, the population, equal to 600,000. So let me write this down here. 2,000 T plus 10,000. Okay. All right, there it is. Notice I wrote P as P of T because it is population really is a function of time T. And they want to know, okay, if the population grows to 600,000, how many hours is going to be required to attain that level of population for this particular bacterium here. So we're going to let this left side be 600,000. And now we're going to have to solve a quadratic equation for the variable T, time. 10,000. And this is 10,000 at the end here. So we got to solve for time T. I'm going to zero this equation out by subtracting 600,000 from both sides. When I do that, I'll have zeros equal to negative 1718 T squared plus 82,000 T. And what's 10,000 minus 600,000? I think that's going to be a minus. That'll be a negative 500 and what is it, 90,000? Is that correct? Negative 590,000. All right, ladies and gentlemen, we're going to solve this quadratic equation by using our quadratic formula. My A is this leading coefficient. B is the 8,000. C is this constant term here. And so here we go. Using the quadratic formula, T is equal to the opposite of B, B being 8,000, plus or minus the square root of my discriminant, which is to say B squared, which is 8,000 squared, minus
82,000.
What, you know, that should be 82,000, shouldn't it? Yeah. Thank you. That should be 82,000, 82,000, 82,000. Yeah, B is 82,000. Minus 4 times A is negative 1718 times C is negative 590,000. And all this sits over 2 times A, or 2 times the negative 1718. All right, I want you to get on your calculator, at least for now. Just give me the discriminant. What does all this evaluate to? What does all this evaluate to here? So, and this should be 82,000 again. Make sure you square 82,000. Yeah, this is 82,000. Tell me what the discriminant evaluates to underneath the square root. Let me know if you get this discriminant here, this quantity.
Okay, I have a number, but it's like giant.
Yeah,
So
okay,
I
go
don't-
ahead, read it off.
Okay, 266952000.
Oh, how would we read this? Ones, tens, hundreds, thousands, 10,000, 100,000s. There's millions, 10 millions, 100 millions, billions. So looks like 2,669,520,000. Anybody else get that?
Yep.
Yeah.
All right, now we're going to have two answers for T. Two different answers. One's going to be the negative 82,000 plus the square root of this big old number here, divided by the negative 3436. And another solution is going to be the negative 82,000 minus the square root of this big old number. And that's divided by the negative 3436. All right, get on your calculator and tell me what this first one evaluates to. And tell me what this second one evaluates to here. I'll run those through our calculator. All right.
8.8.
All right, the first one is like 8.8 seconds. Not seconds, that would be what, hours, correct? I'm sorry about that, it's hours. Yeah, the units are hours. Anybody get the second one here? Dial this one up.
$38.9.
Okay, 38.9 hours. All right. Interesting that we got two different times here. So those would be the two different times that the bacteria culture is at a level of 600,000. Okay, why two different times there? That's interesting. I also want to show you something on your TI-84 calculator here. Let me bring up the machine here. I want to show you something useful. Something that can save you some time. All right, in computing that first one here, this is how we would type it in. I would put parentheses around the whole numerator. So I would say negative 82,000. And then I would say plus the square root of our entire discriminant, which is, you know, you could even type this entire discriminant in the way you were originally seen it, 82,000 squared minus 4 times negative 1718 times negative 590,000. And then a closed parenthesis for the entire numerator, and then divided by the entire denominator, which is to say 2 times negative 1718. Closed parenthesis. And when you do that, you do get the first solution that you did give me, 8.8 hours about. Watch this, ladies. Instead of typing it all over in again to find a second solution, you can just hit second, enter to bring up your previous entry. And now you can just edit this, move your cursor and make one little change. And the only little change you have to make is change this plus sign to a what? A minus sign. Enter. Done. There's your other solution. You see that there? Save tons of time. So whenever you hit second, enter, you bring up the previous entry that you just typed in. And you can then edit that entry. Everybody understand that? What I just showed you there? So you can save tons of time. So the other solution is 38.9 hours. You know, this calculator is even programmable. You can even program in the quadratic formula. And then the program, when you run it, will prompt you for to enter in A, B, and C. And then you hit the enter button and boom, out come your two solutions within about a fraction of a second. This is a programmable calculator. If you hit a PRGM button, ladies and gentlemen, you have programming statements here. You can create a new program. You know, you can call it anything you want. Program. I don't have any code in here, but you can create a brand new computer program in here, and then they give you statements you can enter in write the program for the quadratic formula. I will post a video on Canvas showing you how to program the TI-84 with the quadratic formula. And then it will demonstrate how to run the thing, okay, or how to run the program. I don't mind if you program that in for checking purposes. It'd be awesome to use that. And you can also use that program if you take a course in physics where you have to usually solve a lot of quadratic equations when working with vectors. You can definitely check your answer by, you know, just using your quadratic formula that's programmed in your calculator. All right. You know, in some cases, you might even be able to download an app that already has the program written for you. So you don't have to go through and do all the typing to write the code. But for those of you that are going to computer science, I would recommend that you do look at the code behind the scenes and try to understand what's going on, why the code is the way it is, so that things are done the way they should be done. All right, that's elementary, beginning to understand computer programming. All right, so ladies and gentlemen, we got two solutions. Why is that? What's going on with this thing? Well, what I can show you here is we could have also have solved this equation graphically. So in other words, I could type in this quadratic equation here, and then I would want to find what values of t cause this right side to be equal to 0, because those values of t that cause this right side to be equal to 0 would be the solutions to this equation. Well, the values that cause the right side to become 0 are really called the x-intercepts of this quadratic function when we graph it. And the graph of this quadratic function is going to be a parabola opening downwards. How do I know that? Well, because quadratic functions have parabolic graphs. How do I know it's opening downwards? Because the leading coefficient is negative here. That's why the parabola is opening downwards. And it makes sense that there would be two different times when the population has a level of 600,000. It would be this time here, which is probably the 8.8 hours. And it would be this other time here, which is the 38.9 hours. So you can see why there would be two times, because there's 2 points of intersection between this equation typed in and graphed and this left-hand side equation typed in and graphed. And y equals 600,000 would be this horizontal line. The graph of this is the parabola opening downwards. So there's no small wonder why we got two solutions here, because there's going to be 2 points of intersection between the graph of the right side of this equation and the graph of the left side of this equation. So whether you type this in with this being y1 and this y2 and then looking for the points of intersection, or first of all, getting your equation set equal to 0 and just typing this in for y1 and then finding the x-intercepts, you're going to crank out the same solutions. I'm going to type it in this way on our calculator and show ourselves how we can solve this equation graphically, okay? So let's go back to the calculator and solve this equation graphically. To do that, we hit our y equals button to enter into our equation editing mode. And now I'm going to type in this quadratic function, which was negative 1718. You got to hit this button to enter your variable in. We're not going to use t, we're going to use x in place of t. It doesn't matter what you call the variable. So anyways, we got x squared plus 82,000 t, but I'm going to say 82,000 x minus the 590,000. There we go. Now, when you hit your graph button, you may or may not see your graph because the scaling on your axes could be radically way off. Let's hit graph. We don't see our graph, and that's not surprising. Anyways, I'm going to start seeing your graph. You might want to hit your zoom button. Well, we see one branch of the graph, but to maybe do a better job, hit your zoom button and go down and do a zoom fit. Zoom fit usually configures your X and Y axis appropriately so that you can begin to see the graph of your function or your equation. So just hit zoom fit. Your calculator's thinking now as to what type of scaling to adjust the X and Y axis to. And you can kind of see that we do have kind of like starting to look like a parabola. We still have to tinker with the window though to move our screen so we can see the graph. So I'm going to hit my window button here. Notice my x-axis runs from -10 to 10 by 1. My y-axis runs from a minimum of -150 of -1,581,800 to a maximum value of 58,200 by 1. I'm going to go further out on my x-axis. In fact, I'm going to go all the way out to 100. And let's hit graph now. Okay, the good news is we can start to see the two branches of the parabola. We got to go up higher to see the vertex point though. So I'm going to go back to window and adjust my Y max to go up a little bit higher. Notice it's only 58,000 now. So maybe go up to, I don't know, maybe 100,000. I'm going to space my tick marks on the Y axis by 100 at least. So the resolution is not as fine. Hit graph now. Get a little closer to seeing the vertex point, but we still got to go up higher on the y-axis if you want to see it, the maximum point. And so I went to 100,000, maybe go to 200,000. Y max to 200,000. Wait, did I just do 2? Hold on a second. I wanted 200,000. All right, so 200,000. Okay, here we go. Would you believe I still got to go up higher? Just take it up to 500,000. Y max. Okay, here we go. There we go. All right. Ladies and gentlemen, the solutions to this equation are going to be really the x-intercepts because it's only at the x-intercepts where -1,718 t squared plus 82,000 t minus 590,000 is going to be equal to 0. To find the x-intercepts, we go to calculate. That is accomplished by hitting your second button, followed by your trace button takes you into calculate. And you want to use your 0 function because zeros are another name for x-intercepts. We're going to discover that later in the course. Hit enter. Now to find your x-intercept, you need to move your cursor in the vicinity of the x-intercept you want your calculator to find. I'm going to move it over here to the left. Your calculator wants us to establish a left bound based on how this graph slants as it goes through the x-axis here. I'm going to call this a left bound here by placing my cursor here because it projects up to the x-axis at a point that's to the left of the x-intercept we wish to seek. That's why we call it a left bound. Hit enter. Your calculator wants to now box in this x-intercept with a right bound. To do that, you need to move your cursor a little bit above the x-axis because it projects now down to the x-axis to the right of the x-intercept we want to find. We'll call that a right bound. Hit enter. Hit enter again, and your calculator finds the x-intercept. And there's that 8.8 hours. To find the other x-intercept, we go back to calculate, navigate our blinking cursor over in the vicinity of this right x-intercept over here. To do that, back to calculate, second trace, go down to 0, enter. Navigate that blinking cursor over here in the vicinity of this x-intercept. A left bound, in this case, will have my cursor being above the x-axis because this cursor projects straight down to the x-axis. That's to the left of the x-intercept I wish to find. That's why we call that a left bound. Enter. We now need to box in or bound in this x-intercept with a right bound. So I must navigate my blinking cursor somewhere below the x-axis in this vicinity because now it projects up to the x-axis to a point that's to the right of that x-intercept. That's why we call this a right bound. Hit enter. See how we boxed in the x-intercept? Your calculator needs to box it in to go through a numerical routine behind the scenes to zero in and find that x-intercept. That's necessary to box it in like this. Hit enter again, and boom, there's your other x-intercept about 38.9 hours later. And you can see that it's at those two times the bacterial level reaches a population of 600,000. Okay? All right, so we solved that equation using the quadratic formula, ladies and gentlemen, and we also solved it graphically, okay, by using our graphing calculator. I would encourage you to not only know how to solve it manually, which is probably the more important aspect of the course, but also, be able to solve it graphically too. Convince yourself using your calculator that you can do such a thing there. All right, here's classwork number 1. It's going to be problem number 37 here. I want you to do 37. The distance d in feet required to stop a car that was traveling at a speed of v miles per hour before the brakes were applied depends upon the amount of friction that exists between the tires and the road surface and the driver's reaction time. After an accident, a legal team hired an engineering firm to collect data for the stretch of road where the accident occurred. Based on the data, the stopping distance was modeled to conform to this quadratic relationship between distance and velocity. Okay. Using this distance velocity equation, A, determine the distance that it would be required to stop a car that's going initially at 50 miles per hour at the time the brakes are slammed on or applied. How do you think we would answer this question here? Anybody? Question A is pretty easy to answer. How do you think we're going to answer that? How would question A be answered? Well, I know my velocity in my car at the time of applying brakes is what, 50 miles per hour. So I'm going to let V be what, 50? Just put 50 in for V and crank out your stopping distance. That's easy. Part B, up to what speed to the nearest mile per hour could a motorist be traveling and still have adequate stopping distance to avoid hitting a deer that's 330 feet down the road? In this case, you're going to have to let what be equal to 330 feet? Velocity or stopping distance D? What do you think?
Would it be stopping distance?
So you're going to have to let D be 330, and then you're going to have to solve this quadratic equation for velocity V. Okay, go ahead and do that problem. We'll call that classwork 1. Today is the 31st day of January. Classwork 1, number 37. Okay, anybody get the stopping distance for part A? Traveling at 50 miles per hour, what's your stopping distance?
235 feet.
235 feet. That's almost the length of a football field. And that's probably on a good road here. I don't think there's even ice on this road. It's amazing. All right, now, at what speed will we be able to be traveling at the time of applying the brakes and still be able to just miss deer that are 330 feet in front of our car? Well, we got to set the distance, stopping distance to 330 feet. Then we have to solve this quadratic equation for the velocity of the car. And when you work it all the way down, you end up getting two solutions there to that quadratic equation. So it looks like if we're traveling slower than 62 miles per hour, we're going to avoid the dare. If we're traveling, at 62 miles per hour, it's going to be very close. Okay. This answer, although this is a solution to our quadratic equation, it has no meaning in the context of our problem. We'll throw that one out. So, yeah, you got to be going down the road at no more than 62 miles per hour at the time of applying brakes and still be able to barely miss these deer 330 feet down the road. 330 feet, stop and think, a football field's 100 yards goal line to goal line. That's 300 feet, of a yard being 3 feet. So a football field is only 300 feet long, goal line to goal lines. So traveling at 62 miles per hour, you're gonna, the stopping distance required is actually longer than a football field as far as the goal lines are concerned. All right, did anybody get this answer? These answers for the second part?
Yeah.
Okay. And, that mathematical formula, ladies and gentlemen, that gives you the stopping distance on a road like that, I mean, that would be honored also in a court of law, too. So law does actually admit or allow for science to enter into litigation. Go figure that, huh? Well, there is such a thing as forensic science. Do you agree? And forensics is used to crack a lot of cases too.
Can you show the bottom of that for 1 second?
Okay, what, the flash work right here?
Yeah.
Oh, okay, right there.
Okay, thank you.
All right, so there you go. Okay, ladies and gentlemen, we're done with that section. We got to move on. Last section this afternoon is going to be section 1.6. And again, please do take the time to look at more of those examples in that section 1.5. The author solves other word problems involving quadratic equations. It would be very, very helpful to spend some time in looking through those examples in section 1.5. Section 1.6 is going to have us solving more equations, some of which might be familiar, but then there's going to be some that we've probably never seen before. Okay. All right. So this first equation we're going to try to solve is going to look like this. All right. The good news is this equation is set equal to 0 already for us. And the better news is that the left side is already completely factored. Notice you cannot further factor down w squared minus 7 or w squared plus 4. Because of that, we are good to go here. We can immediately set our variable factors equal to 0 to solve this equation for w. So I'm going to set w squared minus 7 equal to 0, and also w squared plus 4 equal to 0. Now you're probably wondering, what do we do with the 4 out here? I mean, is 4 a solution? No, not necessarily. And to set 4 equal to 0 would not make any sense anyways. 4 is never 0. The only time this left side could be 0 is if these variable factors are 0. That's why they only set these equal to 0. This 4 plays an indirect role in shaping the solutions by having factored it out, okay? But it does not figure directly into these solutions here. Now, to solve this quadratic equation for w, probably the most efficient way would be to employ the square root method, in which case we want to isolate w squared on the left side of this equation by adding 7 to both sides. And then I'm going to take the square root of both sides of this equation. Don't forget to take the plus or minus square root of the number side. Therefore, w is equal to positive or negative square root of 7. There are 2 solutions to this equation right there. Those are 2 solutions. But we still have to find two other solutions by solving this quadratic equation for W. Again, we'll use the square root method by isolating W squared by subtracting 4 from both sides. Now we take the square root of both sides of this equation. Don't forget to take the plus or minus square root of the number side. And therefore we get two other solutions that are W equal to plus or minus what? What's the square root of -4? Anybody? How does this simplify?
2i.
Yes, that's 2i. And so we get two complex conjugate solutions, or two conjugate imaginary solutions, plus 2i and -2i. And we're done. We have solved this equation for its 4 solutions. What would clue me into knowing that this equation has to have 4 solutions? Anybody? How would I know that? Because I did get 4 solutions there. Is that just a coincidence? No, we're on to something big. If you were to multiply that left side out, if you were, which we chose not to, obviously, what would be the highest degree term that I would generate in multiplying this out? This left side. I would generate the highest degree term of being W to the what power? Well, if you take, yeah, W to the 4th power, because W squared times W squared would net us W to the 4th power. And it's not just a coincidence that we got 4 solutions for a 4th degree equation. There is a theorem called the fundamental theorem of algebra, which we're going to run into in the near future, that says when you solve a polynomial equation that possesses integer coefficients, when you solve an nth degree polynomial equation, you're always going to get n solutions. And that's why this is a 4th degree equation. We got 4 solutions. Not just a coincidence. That's the requirement by that theorem. Okay. Another theorem says that if you get any solutions that are non-real, they always occur in conjugate pairs. They always come in conjugate pairs. That's called the conjugate pair theorem. We'll see later on also. Any questions how we solve this for its solutions there? All right, maybe we could try this one here. We got 2y squared times y squared minus 2 is equal to 18 plus y squared. So we want to solve this quadratic equation for the variable w, for the variable y rather. To do so, I'm going to, first of all, have to distribute my 2y squared inside the parentheses here. 2y squared times y squared is 2y to the 4th. 2y squared times minus 2 is minus 4y squared. And this is equal to 18 plus y squared. Now I'm going to zero my equation out by subtracting y squared from both sides. In which case I have 2y to the 4th power minus 5y squared, and that's equal to 18. Now I'm going to subtract 18 from both sides to zero my equation out. Like that. And now, ladies and gentlemen, we have what's called a quadratic form equation. It's not a quadratic equation, but it's quadratic in form. What does it mean to have an equation that's quadratic in form? Well, any equation that looks like this is said to be quadratic in form. Whoops, this should be times x to the nth power plus c is equal to 0. This is called a quadratic form equation. If the leading degree is twice the degree of the middle term, when this polynomial is written in descending order, then we have a quadratic form equation. And quadratic form equations can always be reduced down to ordinary quadratic equations when you employ what is called a U substitution. U substitutions are used all the time in higher level math. Calculus, you'll use them all the time. U substitutions are used to help us see the forest for the trees. They help us take a complicated situation and render it as being trivial so that we know what to do. I'm going to use a U substitution to reduce this quadratic form equation down to an ordinary quadratic equation in the variable u. To do that, I'm going to let the middle variable be equal to u. So I'm going to let u be equal to y squared. But if u is y squared, then this would imply then that u squared is equal to what? y squared squared, which is to say y to the fourth. Isn't that true? So now I can make my change of variable. So this equation now can be rewritten in the form of using the variable u instead of y. So I can rewrite this as 2u squared minus 5u minus 18 equals 0. And ladies and gentlemen, you can see now that we just have an ordinary quadratic equation to solve for the variable u now. Just an ordinary quadratic equation. Furthermore, you know what? We could use the quadratic formula, but we don't really need to. I believe that this trinomial does factor. And how would it factor? Well, you could use the grouping method to factor this if you want to, or you could use a trial and error method. Now, how do I know that that trinomial factors in the variable u? Well, because if you take the product of the leading coefficient and the constant term, you get 2 times negative 18 is negative 36. Now, there do exist two factors of negative 36 that add up to the middle coefficient of negative 5, namely negative 9 and 4. These are factors of negative 36 that sum up to negative 5. So that tells me that this trinomial can be factored. So factoring it using the grouping method now, I will rewrite this trinomial as an equivalent 4-term polynomial, where the middle term, negative 5u, is going to be split up and written as the sum of my decided upon factors over here. So negative 5u, I'm going to rewrite it as negative 9u plus 4u minus 18 equals 0. And now to factor this equivalent 4-term polynomial, I group my first and last 2 terms. That's why we call this the grouping method. Out of the first 2 terms, I can factor out a u. Out of the last 2 terms, I can factor out a 2. And notice I have that common binomial factor, which is a requirement for this technique to work. I can now factor 2u minus 9 out of both the terms, times what would I leave behind? Just u plus 2. And ladies and gentlemen, the left side of this quadratic equation of the variable u has been completely factored. Now that it's completely factored, I will set both factors equal to 0 and solve for u. When I solve this simple first degree equation for u by adding 9 to both sides and dividing both sides by 2, I get u is equal to 9 halves. When I solve this equation for u by subtracting 2 from both sides, I get u is equal to negative 2. But we're not done, because we were not asked to solve an equation for the variable u. We were asked to solve an equation for the variable y. So what I have to do, ladies and gentlemen, when you do a u substitution, you got to remember in the end to back substitute. We got to bring back what we let u be equal to, and we let u be equal to y squared. So now I have to bring that back. So I have to replace u now with y squared here and here. And now we just solve these equations for y. To solve this for y, we take the square root of both sides of our equation. Don't forget the plus or minus square root of the number side. Hence, we have y is equal to plus or minus the square root of 9 halves, which by the quotient rule of radicals, I can break this up like this, which gives me plus or minus 3 over the square root of 2. But we were taught never to leave a radical appearing in the denominator of a fraction, so we're going to have to rationalize this denominator by multiplying the top and bottom of this thing by the square root of 2. And when I multiply the numerator by the square root of 2, I get this. When I multiply the denominator by the square root of 2, square root of 2 times the square root of 2 is the square root of 4. But the square root of 4 is the rational number 2. And there you go. There's 2 solutions to this quadratic equation in the variable, quadratic form equation in the variable y. We just have one more to solve right here. So we take the square root of both sides. Don't forget the plus or minus square root of the number side. Hence, we get y is equal to plus or minus I times the square root of 2. There's your other 2 solutions, and we are done. And so, ladies and gentlemen, we were asked to solve this equation for the variable y. By zeroing the equation out, I discovered that it's a quadratic form equation, and by employing a u substitution, by letting u be equal to y squared, I was able to reduce this quadratic form equation down to an ordinary quadratic equation in the variable u, of which I then solved by using the factoring method, by factoring this left side completely, setting the factors equal to 0, solving for u, then back substituting what I let u be equal to, namely y squared. I can then recover the solutions for y to the original equation, and I'm done. I got my answers. Everybody understand what just happened there? Well, it's on video. That's the good news. So if you missed anything, you can play this to your heart's content. That's the beauty of having this thing be in a virtual format there. So that one's done, and the clock is starting to become an issue. All right, let's see if we can look at another one now. Let's try to solve a different type of equation. This one here is going to be called a rational equation, and we want to solve it for the variable c. So we're going to try to solve this equation for the variable c. That's called a rational equation because it's an equation that contains rational expressions. Rational expressions being fractions. First thing we might want to do is completely factor all of our denominators. Good news, this is already factored. So is this, but this isn't. Anybody help us? How would we factor this easy type of trinomial here? Give me a couple factors of -5 that sum up to -4. And how would this factor? Anybody want to factor this for us? How would this easy trinomial factor?
C minus 5, C plus 1.
Thank you. So -5 and +1 are factors of -5 that add up to -4, the middle coefficient. So therefore, upon factoring that last denominator, our rational equation simplifies to this. This trinomial factors into what you said, c minus 5 times c plus 1. Good. All right, that makes sense so far? All right, now, ladies and gentlemen, that we got all our denominators factored, we need to think about any restrictions that need to be placed on the variable c so as to force this equation to remain defined. And when would this equation ever become undefined? When would it become undefined here? When would I be dividing by 0 if c was ever equal to what? When would this denominator become 0? When c is equal to
5.
5. So we must insist that c minus 5 never be equal to 0.
I'm talking out loud. I have my mic muted.
Oh, okay. No, you're okay. Yeah, so we must insist that c cannot be equal to 5, because if c is 5, then we'll be dividing by 0 here, and the whole equation blows up. It's all undefined. We must also insist that c can never be equal to
-1.
-1. That's correct. This better never be equal to 0, which means c better never be equal to -1. And I think we've already addressed the restrictions for also this denominator by now too. Okay, good. So these are the restrictions. C can never be equal to -1 or cannot be equal to 5. Next thing, we need a common denominator. And my least common denominator must be an expression that's going to be divisible by all my denominators. Being the case, I must have a c minus 5 in it. Also must have a factor of c plus 1. And we've accounted for all our factors to be divisible by this denominator. Now we're going to take that LCD and multiply both sides of our equation by it to eliminate all the fractions. So here we go. I'm going to take this c minus 5 times c plus 1. And I'm going to multiply it by this fraction. Got to multiply this fraction by the common denominator also. Now this step is kind of laborious, but it is an important step, so please do show it on your paper. And this is going to be equal to the right-hand side fraction must be multiplied by the common denominator. So that's to say, I'm going to have to put it down here a little bit. C plus 1 must be multiplied by the right-hand side also. All right, now the purpose of this is to get rid of all the fractions. What cross cancels out here or reduces out here? The c minus 5s drop out, and we're left with 4c multiplied by c plus 1. fraction gone, minus. Here, the c plus 1s drop out, reduce out the 1s, leaving us with 1 times c minus 5. Now, it's very important to enclose the c minus 5 inside parentheses, because if you don't, that's going to be an error, because we are to subtract off c minus 5, not just c. And that's equal to what over here? What cross cancels out here? You know what? This should be c minus 5 here. C minus 5 times c plus 1. I do apologize. Well, the c minus 5s drop out. C plus 1s reduce out. And we're left with 3c squared plus 3. All right, ladies and gentlemen, now we got no more fractions, but we still have to solve the quadratic equation. So distributing this 4c in here, I get 4c squared plus 4c. Distributing the negative 1 in here, I got the minus c plus 5. And this is equal to 3c squared plus 3. Combining the two middle linear like terms, we get 4c squared plus 3c plus 5 equals 3c squared plus 3. Zeroing this equation out, I'm going to subtract 3c squared from both sides. I'm also going to subtract 3 from both sides. By doing these two operations, I get my equation set equal to 0 on the right. This reduces down to 1c squared plus 3c. 5 minus 3 is plus 2, and this is equal to 0 on the right. And now we have a very simple quadratic equation to solve. You could use the quadratic formula, but you don't really need to. This is a very easy trinomial to factor. Two factors of 2 that add up to 3 would be 1 and 2. So this thing immediately factors into c plus 1 times c plus 2. And notice again, just to qualify to be factorable, a trinomial needs to be quadratic in form. This degree is twice the middle degree. We call that quadratic in form, and that's why it factors into the product of two binomials. If this was a third degree term and this was a first degree term, this trinomial would not factor into the product of binomials. It has to be quadratic in form. So either this degree has to be 2 and this 1, or this degree has to be 4 and this 2, or this degree would be 6 and this would be 3. Those would be quadratic form trinomials. Okay. Now we set these equal to 0. So c plus 1 is equal to 0 implies that c would be equal to negative 1. Or we set c plus 2 equal to 0 and solve this simple equation to get another solution as being negative 2. Ladies and gentlemen, one of these solutions has got to go. Which one? We got to toss it out.
Negative 1.
Why do we have to toss out negative 1? This is not a word problem. What's the problem here?
It's one of the restrictions.
It violates this restriction we had to place way back at the beginning here. So remember, we said c could never be equal to negative 1 or else the whole equation is undefined. Well, guess what? We went through the solution process and got negative 1. We must toss this out. The only solution is negative 2. And that is it. Okay, so don't forget, if you have a variable pairing in any denominator of a rational equation, make sure you state your restrictions and check in the end to make sure none of your solutions violate any of your restrictions. That's very important there. So there you go, ladies and gentlemen. We solved that rational equation for C. That's a classic one there. All right. All right. Moving on, as it's 1:51 now. Clock keeps burning. How about absolute value equations? Have you ever solved any of those? Well, I know if you've had intermediate algebra here at Mott Community College that you have solved some absolute value equations. I don't know if you're coming in from some other institution or placed into this course. I'm not sure. I'm hoping that you have, but it's no big deal because it's pretty easy to pick up on. All right, this is called the absolute value function of mathematics, and how does it work? Well, when you take the absolute value of a number, basically the result is the number of units that number is away from 0 on the number line. So 4 is how many units away from 0 on the number line? 4 units. So the absolute value of 4, we say, is equal to 4. What's the absolute value of negative 4? Well, negative 4, albeit to the left of 0, is still 4 units away from 0. So the absolute value of negative 4 is 4. In fact, ladies and gentlemen, when you take the absolute value of any number, it always reports the positive of that number. That's how the absolute value works. Okay. All right. So if I give you this equation, the absolute value of x is equal to 10. Can anybody tell me what a solution to this equation would be?
Be negative 10 or 10.
Yep. X could be equal to positive 10 because the absolute value of positive 10 is 10. Or, however, there's another solution. X could be negative 10 because the absolute value of negative 10 is 10. So this equation has two solutions. Notice that. So in general, this is how we should think about solving absolute value equations. If I have a positive real number, and if I have in general the absolute value of x or some expression in x, or it could be some other variable, and if I have that equal to c, well, this is implying that I'm going to have two possible solutions. X has to be either positive c or x has to be equal to negative c. So here's how we solve absolute value equations. First of all, and this is extremely important, you must first of all isolate your absolute value on one side of your equation. And once you isolate your absolute value, and only after you isolate your absolute value on one side of your equation, then, ladies and gentlemen, we can drop our absolute value symbols and set what's inside of it equal to either the positive of the number side or the negative of the number side. And then we'll have to solve any resultant equations thereafter. Okay? So you always try to isolate your absolute value on one side of the equation before you do anything else. Try not to forget that. It's often forgotten. Any questions about that? Here's a special case. This is one you want to lock away in the memory banks. And it makes sense why this is the way it is. Suppose I take the absolute value of some quantity and I have it set equal to a negative number. What would I conclude about the solutions to this equation? Anybody want to weigh in? What kind of solutions would this absolute value equation have?
Does it not have any?
You're correct. There would be no solution to this equation. It's a special case. There's no solution because think about it. If you take the positive absolute value of anything, you're always going to get a positive. And a positive can never be equal to a negative. There would be no solution to such an equation. So if you run into one of these, you need go no further. Just write no solution. All right. So that's a special case. Once in a while, that might pop up. All right, let's try to solve one here. Let's see here. I have this one in mind. We will try to solve this absolute value equation for the variable t. Want to solve for t here. Warning, ladies and gentlemen, can I distribute this 4 inside the absolute value?
No.
The answer is no. Don't do that. You cannot distribute a factor outside an absolute value into the terms inside the absolute value. You cannot do that. Don't confuse absolute value symbols with parentheses. Now, if I had parentheses around here, yes, I could distribute the 4 inside the parentheses, but these are not parentheses, so don't do that. No, we need to isolate the absolute value on the left side of our equation. So what would be the first move in isolating my absolute value? First move.
Divide both sides by 4.
We could, there's nothing wrong with that. We could do that, but then we're going to start introducing fractions over here. Do you agree we'll have a fraction? Is there anything else we could do besides dividing by 4 yet? Let's hold off on dividing by 4. Anything else?
Subtract 2.
Let's just move the constant over to the right first. Hold that thought about that 4, though. And this is equal to 20. Now, what do? Go ahead. We now divide both sides by what? By 4. You are correct. Okay, so now we divide both sides by 4. and we will isolate our absolute value there. 4 is dropped. We're left with our absolute value all by its lonesome, and that's what we wanted. And on the right, we do thankfully get a nice whole number here. Now, ladies and gentlemen, since we have our absolute value isolated, we can drop, and notice this is not the special case either. So we can drop our absolute value symbols, and we take whatever inside the absolute value, which is 2t plus 7, and I set it equal to either positive 5, or I set it equal to what? Negative 5. Everybody see that there? And now we have 2 equations to solve. And these are just simple first degree equations. So we subtract 7 from both sides, divide both sides by 2, and we get t is equal to negative 1. That's one solution. Solving this equation for t, we minus 7 from both sides. We get 2t is equal to negative 12. Divide both sides by 2, and another solution is negative 6, and we're done. We have our 2 solutions. We have our 2 solutions to that absolute value equation. Everybody understand how we just solved an absolute value equation for its 2 solutions there? The key is always try to isolate your absolute value first before you drop your absolute value symbols. Must have it isolated on one side. All right. So that one's good there. Any questions about that? Almost 2 o'clock. 1 minute, less than a minute. Now, initially, this looks like a nasty problem, but what would be the first move here to solve this absolute value equation? We want to try to isolate what? The absolute value. So what would we do?
Move the 7 to the other side.
All right. We're going to subtract off 7 from both sides. And we're left with negative 1 is equal to the absolute value of 9z minus 3. Why need I go no further?
No solutions.
There is no solution to this equation because you cannot take the positive absolute value of anything and generate a negative. There's no solution, and we're done with this problem. So just keep that, special case in mind if it ever pops up. One last type of absolute value equation is this one here. Ladies and gentlemen, what if I have the equivalence between 2 absolute values? How would I solve such an equation as this? What if I have the equivalence between 2 absolute values? How do we solve such an equation? Well, you got to admit, we do have our absolute value isolated at least on one side of our equation. In fact, it's isolated on both sides. Being the case, we can immediately drop our absolute value symbols. And we can grab one of the sides. I like to use the left side always. That's just me. I like to say that this 4d minus 3 is going to have to either be equal to the positive of this or the negative of this. So I would say this 4d minus 3 is either going to be equal to the positive of this 3 minus 4d, or this 4d minus 3 has to be equal to the negative of this 3 minus 4d. There you go. That's in general how you handle the equivalence between 2 absolute values. So in general, when you got like the absolute value of x equal to the absolute value of y, you can drop your absolute value symbols and you can say that x must be either equal to positive y or x must be equal to negative y. In general, this shows you how to solve an equation where you have the equivalence between 2 absolute values here. In general, that's what we do. Okay, that's what I did above here. Now we got to solve this equation. So we got 4d minus 3 is equal to 3 minus 4d. I'm going to add 4d to both sides to bring my d to the left. In which case I got 8d minus 3 is equal to 3. Add 3 to both sides. And therefore I get 8d is equal to 6. Divide both sides by 8. And d walks out of this with a value of 6/8. But 6/8 reduces down to 3/4. And so one solution is 3/4 here. D is equal to 3/4. Not done though. I still got to solve this equation over here for D. So we got 4d minus 3 distributing the negative sign or the negative 1 inside the parentheses here. I'm left with minus 3 plus 4d. Now, solving this equation for D, I would subtract 4D from both sides of my equation, and something weird happens. What happens? What happens to my D? It drops out on both sides, and I'm left with this numeric statement. Is this a true or false numeric statement? That's true. Yeah, that's true all day long. And so, ladies and gentlemen, we would conclude that this equation has what type of solutions? Anybody?
Infinite.
Yeah, it has all real numbers as its solution set. So the solutions to this equation are all real numbers. That's an infinite number of solutions. Well, what do you think we're going to do with this lonely 3 forces being a solution and all real numbers being a solution of this equation? We're going to join these sets together, because OR means, ladies and gentlemen, union, joining sets together. So what's the union of 3 force being a solution to my absolute value equation and all real numbers being the solutions to my absolute value equation? The union would be all what? All real numbers. Do you agree? So the solutions to this equation would be all real numbers. All real numbers are solutions. So it doesn't matter what number you put in for D here and here, the left side will always be equal to the right side. This is called an identity in mathematics, when the left side is equal to the right side for any value of the variable. So all real numbers are solutions to this equation here. But nonetheless, it still shows us in general how to solve an equation where you have the equivalence between absolute values. All right, got to move on. Done with the absolute value equations. Next type of equation I want to show you how to solve is called a radical equation. An equation that has a radical in it. Want to solve this equation for x. To do so, ladies and gentlemen, just like with absolute values, when you have a radical equation, you always want to try to isolate the radical on one side of the equation. Isolate the radical on one side of your equation. Very important. Well, we're lucky here because we already have our square root isolated on the left side. Now to solve this equation, therefore, we're going to have to get rid of this square root. The only way you get rid of a square root is by squaring it. So now we're going to square the left side of our equation, but if I square the left side, I must also square the right side of my equation. So we square both sides of this equation. When you square a square root, it disappears, and so the left side trivially just becomes 7x plus 8. The right side is not so trivial. We're going to have to FOIL out this product of these two binomials here. I've got to multiply this out. X times x, x squared. X times 2 plus 2x. 2 times x plus 2x. 2 times 2 plus 4. And so we really see that we have to solve a quadratic equation now. So we have 7x plus 8 is equal to x squared. Combining the two middle like terms, we got plus 4x plus 4. To solve this quadratic equation, let's zero the equation out. So to do that, we would subtract 7x from both sides and minus off 8 from both sides. When we do that, the left side goes to 0 and the right side is going to be x squared. What's 4x minus 7x? Minus 3x, and 4 minus 8 is what? Negative 4. Got a question for you, ladies and gentlemen. Can we solve this quadratic equation by factoring instead of using the quadratic formula? It's faster if you can factor. Can we factor this trinomial? The trinomial would factor into
x minus 4 and x plus 4. Or x plus 1.
Exactly. Now we set our factors equal to 0 and then solve for x. Two simple first degree equations here. So we get one tentative solution as being 4. You'll see why I'm saying the word tentative. And another tentative solution is negative 1. There we go. Now, ladies and gentlemen, you need to make a note and highlight this in your notes so you don't forget this. We're not done. When you solve an even root equations, you need to always check your answers. So just highlight this. Even root equations must be checked. In the end, you got to check them out, okay? You got to make sure your solutions work in the original equation. Because sometimes when you go through the solution process and solving an even root equation, like the square root equation, you can generate false solutions. It does happen from time to time. Now, when you're solving an odd root equation, like a cubed root or a fifth root or a seventh root, you don't have to check your answers. But when you solve an even root equation, like a square root or a fourth root or a sixth root, you need to check your answers. So unfortunately, we're not done. We need to take this 4 here and check it out. Put it back in here for x and here for x and make sure it satisfies the equation. So here we go. We will check x equals 4 by putting 4 back in for here and here. So we ask ourselves, is the square root of 7 times 4 plus 8, is that equal to 4 plus 2? Does it check out? 7 times 4 is 28. 28 plus 8 is 36. So is the square root of 36 equal to 6? Is that true? Looks like it checks out, doesn't it? So we retain 4 as a solution. We got to check -1 though. Take -1, substitute it back in the original equation and for x and verify, does it satisfy the equation? Is the square root of 7 times -1 plus 8 equal to -1 plus 2? Is that true? 7 times -1 is -7, and -7 plus 8 is 1. So is the square root of 1 equal to 1? Is that true? It looks like it checks out. So therefore, we do retain both of these as solutions. But be on guard. You never know. I may slip one in the future, ladies and gentlemen, whereby if you don't check your answers and don't toss out one of your answers or toss out both of them, you might get into trouble. So just make sure you check in the end when you're solving an even root equation. Make sure your solutions check out the original equation. If they do, retain them. If they don't, you have to toss them out. Okay?
Just curious, can I ask why that happens?
Well, it happens. I'll show you why it happens. Let me just show you a simple example here. If we have the square root of x is equal to -1, you and I both know that you cannot take the positive square root of anything and generate a negative, correct? So we can see this is dead on arrival already. It has no solution. Suppose we just went through the song and danced to squaring both sides. The problem is when you square both sides, you might also be squaring a negative. And when you square a negative, it walks out as being a what? A positive. And now the problem is when you go back to check your answer, it's not going to hold water because you put the 1 back in here for x. The square root of 1, positive square root of 1, is not equal to -1. It doesn't work. Do you agree? So because we're taking a positive square root here and it's equal to a negative quantity, we would suspect right off the bat that this is a contradiction. And you can clearly see it play out when you try to go through, the solution process, that it doesn't work out in the end anyways. It doesn't check out. So I don't know. Does that answer your question there?
Yeah, thank you.
All right. So radical equations, try to always isolate the radical on one side and then raise your equation, both sides of your equation to an appropriate power to eliminate the radical. Okay. 11 minutes passed already. All right. Let's try this one. We have 2x minus 1 raised to the 3/2 power. Minus 3 is equal to 122. We will try to solve for x. This gives us a different look. This really is a radical because raising a quantity to a fractional exponent really is equal to a radical. Recall the definition of rational exponent. X to the m over n power is really like taking the nth root of x to the mth power. So you can see that a rational exponent really is a radical by definition. And so, ladies and gentlemen, we're going to try to isolate this on the left side of our equation. To do that, I'm going to add 3 to both sides. Therefore, I have the 2x minus 1 raised to the 3/2 power is equal to 125. Now, the most efficient way to solve for x here is to get rid of this exponent. In other words, turn this exponent into 1. Well, what power would I have to raise the left side and the right side of my equation to accomplish that? Remember, when you raise a power to a power, you multiply exponents. So what would I have to multiply 3/2 by to make it 1? What would you multiply 3/2 by to make it 1? It's what? It's reciprocal. Let's raise the left side of this equation to the 2/3 power, but that means I got to raise the right side of my equation to the 2/3 power. Now, raising 3/2 to the 3/2 power to the 2/3 power means you multiply these exponents, and these are reciprocals, and the product of reciprocals is always 1. So this is always going to give you 1. And therefore, we have 2x minus 1 to the first power equal to 125 to the 2/3 power. Ladies and gentlemen, if you get on your calculator and take 125, raise it to 2/3 power, you'll discover the result is going to be what? 25. Reason being is because 125 to the 2/3 power is like taking the cubed root of 125 first and then squaring that result. But the cubed root of 125 is 5, and then 5 squared is 25. That's why it's no small wonder that if you take 125 and raise it to the 2/3 power, you're going to get 25. Now we just solve for x. Add 1 to both sides. We get 2x equals 26. Divide both sides by 2, and x is what? 13. And there we go. We're done. So your solution is x equals 13. So that one is done. Everybody see how we did that one there? Okay. 2v plus 7 raised to the 2. Not the one I want. Scratch that. This is the one I want to solve here. Wait a minute. Hold on a second here. Okay. Hold on 1 second here. Not sure what's the problem here. Okay, this is the one I want to solve right here. Oh, really? I just had it. All right, let's try this one here. If I have 2v plus 7 raised to the 2/3 power minus v minus 2v plus 7 raised to the 1/3 power minus 2 equals 0. So we want to try to solve this this equation here. I got a question for you, ladies and gentlemen. Let's get back and look at the forest for the trees. Do I have a quadratic form equation? Is this degree twice my middle degree? Is 2/3 2 times 1/3?
Yeah.
It is. So we have what's called a quadratic form equation here. It's not a quadratic equation. It's called a quadratic form equation. And with a u substitution, I can reduce this down to an ordinary quadratic equation. So this is called a quadratic form equation. Here we go. I'm going to let u be equal to this middle variable term here. I'm going to let u be equal to this. And therefore, u squared is going to have to be equal to this. So therefore, I'm going to let u be equal to 2v plus 7 to the 1/3 power. And therefore, u squared is going to have to be equal to 2v plus 7 to the 2/3 power. So this equation now collapses down to an ordinary quadratic equation in the variable u. I'll have u squared minus u minus 2 equals 0. And you got to admit, this quadratic equation in u looks so much simpler than this one up here. That's the intention of a u substitution, is to take a very complicated situation and to trivialize it so we can clearly see how to approach it then. Ladies and gentlemen, can I factor this trinomial? Give me a couple factors of -2 that sum up to -1. That would be -2 and 1. So this trinomial factors into u minus 2 times u plus 1. Now we set both these factors equal to 0 and then solve for u. So we get u is equal to 2 and we get u is equal to -1. But we were not asked to solve for u. We were asked to solve for v. So we have to back substitute now. Back in for u, we got to bring this back. This must be brought back now and must replace u down here and here. So therefore, we would have 2v plus 7 to the 1/3 power is equal to 2. And 2v plus 7 to the 1/3 power is equal to -1. We now have to solve both these equations for v. All right, so how do we solve these for v? Let's solve this equation for v. How do I get rid of the 1/3 power? I have to raise this to the 3rd power, do I not? Do I not have to cube both sides to get rid of this rational exponent? So I will cube the left side of my equation. But if I cube the left side, I must cube the right side. Now, when you cube the left side, you multiply these exponents, but 1/3 times its reciprocal, 3/1 is 1. So we just have 2v plus 7, and that's equal to 8 on the right. Solving for v, subtract 7 from both sides, we get 2v is equal to 1, so v is equal to 1/2. So there's one solution, 1/2. But we also have this other equation to solve, and we will accomplish it the same way. We will cube both sides of our equation. So I cube the left, I cube the right, and therefore these exponents drop out of the picture to 1, and we have 2v plus 7 to the 1st power, which is just this, and -1 cubed is -1. Subtract 7 from both sides, I get 2v is equal to -8, and therefore v is equal to -4. And there's another solution there. And ladies and gentlemen, we are done. And we don't have to check our answers because our original equation really had what? Cubed roots. This is a cubed root. So is this. These are cubed roots. These are odd roots. So you don't have to check your answer. And that's why we have our results there. Okay. This is called a U substitution. A U substitution, that's what happened here. A U substitution is designed to take a complicated situation and render it trivial or discernible. And U substitutions are used all the time in calculus to help you do that when you're trying to differentiate or integrate various functions, okay? Questions on this problem here? Solving a quadratic form equation by employing a U substitution. Well, I'm all out of time, ladies and gentlemen. It's 2:20, and I do appreciate your patience and interest this afternoon. If you have any other questions, I'll remain on the line. Now, I only gave you, unfortunately, I think one classwork, and I do apologize. Just kind of ran out of time, you know. But you guys have a great, safe day, and hopefully I'll see you in a couple of days. Remember now on Alex quizzes, I will allow you 2 takes on it and take the highest of the 2 scores. And that will be for the remainder of the semester on Alex quizzes, okay? And it'll be a quick retake where you don't have to retake the whole quiz. It only allows you to retake the ones you got marked wrong, which is nice. That's not a bad day. I mean, a bad thing. Yes, you have a great day too. Somebody just texted me. All right, ladies and gentlemen, take care. I'll see you in a couple of days. I'll be on the line if you have any questions or comments or anything.
I had a question about the Zoom meeting recordings, because when I click on it,